Good. Hi, everybody. I'm Stephanie O'Brien. I teach at Comac High School, and today we are going to get started in reviewing redox and electrochemistry. So bear with me while we switch screens. Okay, so here's our goals for today. What I'd like to do is just go over the major points you need to know for redox and electrochemistry. And then I have basically I took the last 6 or 7 Regents exams and I pulled out every question as it relates to redox and electrochemistry. So we'll go through how I would answer those questions. And then we'll keep the chat going. And if there's questions coming through the chat, you could send them there, or you could, if you'd like to join this Remind group, you could text 81010 with the message with the text at ChemLive. Alrighty? So either way, whatever works for you, we'll keep the chat. We have some teachers up on the chat right now, so if you want to ask questions, feel free at any time during the session to get going. Alrighty? Let's go. All right, so our topic is redox and electrochemistry, and basically this topic is going to look at any chemical reaction that either uses electricity or produces electricity. So if we look first at the history, chemists thought that oxidation was anything that basically just involved combining something with oxygen. Today we kind of have expanded our definition of oxidation and reduction, and we understand it as anything that involves a transfer of electrons. So to have transfer of electrons, a substance is going to lose an electron and another one is going to gain one. But regardless, we're going to have some type of conservation of charge. So instead of us saying oxidation and reduction reactions, it seems like it would actually be like a tongue twister to keep saying that over the course of the unit. We condense it and we just call them redox reactions. So one of the questions that came in already was asking about what a redox reaction is. Redox just means that we're combining those terms, oxidation and reduction, and we're going to go through what each of those mean. Okay, so oxidation is when you lose an electron and become positively charged. Your oxidation state is going to go up. So sometimes people are a little bit confused about this, why when you lose something you become more positive. But most of us are familiar with, at least in math, that if you subtract a negative number, you're really just adding, or become, something will be positive. So minus and minus means positive. The same is going to apply here. When you lose an electron, which is negative, you're going to become positive, and your oxidation state will go up. Reduction is when you gain an electron, and there's going to be a reduction in your oxidation state. And again, something that bothers people, that what do you mean by saying that I'm reduced, but the oxidation number is going down? So, just keep that in mind, that the oxidation numbers, we're going to go through how to figure them out, and we'll try to help you along the way to figure out tricks to make that a little clearer. So oxidation and reduction always occur together. You can't have one without the other. It's a simultaneous process. So that's what that word means. Sometimes people ask, what does simultaneous mean? They're both happening at the same time. So if something's oxidized, at the same time, something is going to be reduced. So for us to figure out what's being oxidized and what's being reduced, we need to have some type of system. And the system that we use is this kind of annoying system, but it's the use of oxidation numbers. And do you have to memorize them? Well, you have a reference table to help you, but you really have to have an idea of what the oxidation numbers are, or the rest of the unit becomes extremely difficult. So we'll take time. We'll try to go through each one slowly. At this point, though, you really need to have a reference table out in front of you, opened up to the periodic table, so you can see what we're talking about as we go through. We're going to assign oxidation numbers to every atom, and the reactants and the products. So here we go. This part's a little bit boring, I apologize, but we'll get through it. All right, oxidation numbers. if you are an element and you are all by yourself, you're going to have an oxidation number of 0. So if we look at the example here, we have Na plus Cl2 gives you 2 NaCl. If you look at Na is all by itself. Since it's all by itself, it has an oxidation number of 0. So when you see an atom, anything that has no charge is going to be 0. Cl2 is also by itself, so we'll have an oxidation state of 0. So when you're all by yourself, your oxidation state is 0. Sometimes we forget and we just want to go look at our reference table. Just first thing you want to do, is it by itself or is it combined in a compound? Next, monatomic ions. That means if you're looking at an element and it has a charge in the top right-hand corner, an ion, remember, is something that has a charge. If it has a charge, the oxidation number is equal to that charge. So for example, if I have Fe plus 3, the charge is going to be plus 3. If I have an oxidation number of, if I have the element ion, I'm sorry, Br minus 1, the oxidation state is going to be minus 1. If you look at your reference table and you're opened up to the periodic table, every metal in group 1 is always going to be plus 1. You can see that just by looking at the top right-hand corner of each box. You see that everybody in group 1 is plus 1. If you're in group 2, you're going to have an oxidation number of plus 2. Fluorine is always minus 1. Other halogens are also minus 1, when they're the most electronegative element in the compound. Hydrogen is plus 1, and it's typically going to be written first when it's plus 1, although not always. But hydrogen is usually going to be plus 1. It can be minus 1, though, and that's in the case when it's a hydride. So if you look at the example, you have HCl. H is plus 1, and Cl is minus 1. And the H is written first. And then in the second example, LiH, you have Li is plus 1 and H is minus 1. It's a hydride. Oxygen is always minus 2. But there are 2 exceptions for oxygen, so we just want to go through those for you to be aware of. When oxygen is combined with, when oxygen is combined with fluorine, it's plus 2. So F is minus 1 in this example, and there are 2 of them, so it's minus 2. So O is going to be plus 2. Oxygen could also be minus 1 when it's with a peroxide. So in H2O2, you have H is plus 1, and there are 2 of them, so plus 1 times 2 is going to be plus 2, and it has to have the oxygen being negative 2 to add up to 0, so each O is going to be minus 1. This is what we call peroxide, and you'll notice that you see this general kind of formula like X2O2, and then in that case, instead of O being negative 2, it's negative 1. So H is plus 1 in that case, and then O would be minus 1. So it also happens in the case of Na2O2, where Na is plus 1 times 2 is plus 2. So you have to have the oxygen adding up to negative 2. Each O has to be minus 1. Next, we need to know that in all compounds, the charges must add up to 0. So when you're looking at what we were just doing with the peroxides there, the charges were totaling 0. So here's an example of calcium chloride. Calcium is in group 2, so it's going to be plus 2. So that means that the total charge of all the chlorines has to be minus 2. So when we look at that, we can see that if chlorine is plus 2, and there's only one chlorine at plus 2, the calcium is plus 2, the chlorines have to add up to negative 2. Each chlorine is going to be negative 1, because negative 1 times 2 is going to give us negative 2. Okay, for a polyatomic ion, the sum of the oxidation numbers must equal the ion's charge. So if you have, for example, SO4, oh, we have a lag, I'm sorry. Okay, so for SO4 minus 2, the sum of the charges must add up to minus 2. So instead of adding up to 0, like a normal compound will add up to 0, but if there's a charge in the top right-hand corner, you're going to make sure that the sum of all the oxidation numbers adds up to that number. So here, oxygen has an oxidation state of negative 2 times 4, because there are 4 of them, adds up to minus 8. Sulfur, if it was a neutral compound, would be plus 8, but since it has to add up to minus 2, the sulfur is going to be plus 6. So just keep an eye in the top right-hand corner. Notice if you have a charge. If you have a charge, you want to make sure instead of adding up to 0, it adds up to whatever that charge is. So what I want to do is just take a break for a second, and going to give you a chance to just try a couple of examples. There's 4 examples here. Just fill in what you think the oxidation state will be for each of these elements. Okay, we got a question came in through our Remind asking about the difference between oxidation number and oxidation state. You could really say either one. It really doesn't matter. So either one is fine. So we'll go through these examples. We have bromine is going to be 0. It's all by itself. Even though there are 2 of them, it's just an atom. Atoms always just have a charge, no charge, just 0, neutral. K is a monatomic ion, so it's going to be +1. We have MgSO4. So when you look at a compound, one of the things that students are asking are, how do you know which one to assign first? So if you have MgSO4, you're going to start with the ones that we gave rules for. So we just gave you a list of rules. You're going to figure out the one that you don't have a rule for by adding it up to 0. So if we look at MgSO4, well, we know oxygen is -2. -2, and there are 4 of them. So -2 times 4 is -8. Mg is +2. Since it has to add up to 0, that sulfur is going to have to be +6. So we didn't have a rule for S. There was no rule for S when we went through those rules. So figure out Mg, figure out O, and you figure out the unknown one by making sure that the sum of all the numbers adds up to 0. And then we have Na. Na again is all by itself, so going to be 0. All right, so now that we had a little discussion about oxidation numbers, what we want to do is start to figure out, when we look at an equation, how do we figure out what's oxidized and reduced? So if an atom loses an electron, the oxidation state is going to become more positive. When you gain an electron, you're going to become more negative. So we use this acronym, Leo the lion goes grr. Some people like this other one, oil rig. This is the one I prefer, and I think this is the one that's most effective. So this is the one that we're going to go with. Leo the lion goes grr. What does that stand for? When you lose electrons, it's oxidation, and you gain electrons, it's reduction. So just using the acronym will at least give you the definition of what the word means. Oxidation is losing electrons, reduction is gaining electrons. All right, then we have these arrows. So I like to use these arrows for 2 reasons. We'll talk about the first one here. When you lose electrons, you're going to become more positive. So if you were to envision a number line, when you're becoming more positive, you're kind of moving to the right on the number line. So if you're oxidized, the number is moving from the left to the right. When you're reduced, you're going down the number line. So your oxidation number is moving down or to the left. So here's an example. Mg plus S yields Mg plus 2 plus S minus 2. And what you first want to do is, when you're trying to figure out what's oxidized or reduced, is assign your oxidation numbers. So I'll give you 1 minute to figure out what we should have right up top for the oxidation numbers. So you write right above each element in the ion and the compound, what are the oxidation numbers? Okay, so here we would have Mg is 0 on the reactant side, it's an atom. S on the reactant side is an atom, it's 0. On the product side, you have a magnesium ion, so a charge of +2, because monatomic ions, you just take whatever the charge is. The sulfur ion charge is -2. Now what we want to do is we want to look at what's happening as we move from the left to the right across the equation. So the sulfur is going from 0 to -2, and the magnesium is going from 0 to +2. So if you think about a number line, magnesium 0 to +2 is becoming more positive, so it's being oxidized. Sulfur is going from 0 to -2, so it's going down the number line, so it's going to be reduced. So in summary, to figure out when something's oxidized, the oxidation number has to go up. You're going to become more positive in oxidation number because you're losing electrons. Losing electrons makes you more positive. Reduction is when the oxidation number goes down, you're becoming more negative. So you're gaining electrons. So again, we're just going to take a second. I want you to, before we go further in evaluating our redox reactions, we're going to just take a second to make sure that you understand how to assign oxidation numbers and how to identify when something's oxidized or reduced. So take a second to try this problem. Okay, we got a question came up through the Remind feed asking what monatomic means. Monatomic, when you're looking at an element, just means like one capital letter would probably be the easiest way to recognize it, and there's no number on the bottom. So for example, anything that's not diatomic, obviously is monatomic, but diatomic, there's a whole bunch of ways your teacher might have taught you diatomic. Some people use Brinkelhoff or Hofbrinkel, but monatomic means that you do not have, you're not diatomic, just one capital letter, no charge. Or you could be a monatomic ion, could be a single capital letter with a charge. Okay, so K2Cr2O7, we have a rule for potassium, we have a rule for oxygen, we don't have a rule for chromium. So I'm going to figure out chromium last. When we look at this, oxygen is -2. There are 7 of them, so -2 times 7 is -14. K is in group 1, so it's +1 times 2 is +2. So we got to figure out what this chromium is, and we know that it has to add up to 0. So chromium, the sum of the chromiums would be +12, which means each chromium would be 6. When the Regents is asking for the oxidation number, we're looking for the number on top. So the way that I set it up here, everybody kind of does it different, but we're looking for the individual oxidation state. So each chromium is +6. Okay. The second example says, which of the following shows oxidation? So oxidation means that you're going to become more positive. Your oxidation number needs to increase. So when we look at each of these, the one that shows increasing oxidation number, let's see if this will go for us, is going to be choice 2. Cu goes from +1 to +2. Okay, next I just want to look at one more example. If we have, again, which one is showing you reduction? We said that reduction is when you gain electrons, which means your oxidation number is going to go down. So if you look at each of these, the one showing reduction would be choice 3. Mn goes from +4 to +2. All right, next, one of the questions that came in ahead of time was they asked how you identify what a redox reaction is, because there are a bunch of Regents questions that will say which one of the following represents a redox reaction or an oxidation reduction reactions. For something to be a redox reaction, there has to be a transfer of electrons. Something has to be oxidized and reduced. What you are going to see in a problem where there's a redox reaction is that the oxidation numbers are going to change. If all the oxidation numbers stay the same, not redox. So double replacement will never be redox. You're going to look for something like a synthesis, decomposition, or single replacement reaction to be a redox reaction. So another way that we typically tend to identify it, not that it's the best way, but if you could see something all by itself on one side of the arrow, that's going to be a redox reaction because it's going to have a charge of 0 as long as on the other side it's combined. So what I want you to do is take a second and assign oxidation numbers to the elements and compounds in this equation right here. And what I want you to do is see if you could just figure out which one is becoming more positive, so oxidized, and which one is becoming more negative and reduced. Okay, so if we fill in our oxidation numbers, carbon's all by itself, 0. Oxygen's just an element, again, by itself, 0. And then on the product side, oxygen is -2 times 2 is -4. So the carbon is going to be +4 and the oxygen is -2. So which substance is oxidized? You look at what the element has an oxidation state of on the left and what is the oxidation state on the right. So let's look at carbon. Carbon is going from 0 to +4 and oxygen is going from 0 to -2. The one that's oxidized loses electrons, so becomes more positive. So carbon is going from 0 to +4, lost electrons, so it's oxidized. And which element is reduced would be, well, oxygen's going from 0 to -2, so it's being reduced. Remember, though, in a question, if they were to ask you which substance is oxidized or which substance is reduced, always pick the one on the reactant side of the arrow. Okay, here's another example. So again, what I'd like you to do, take a minute to assign the oxidation numbers across the top, figure out what's oxidized and what's reduced. Okay, so going across, copper's all by itself. Then we have AgNO3, oxygen is -3. Oxygen is -2 times 3. -6, silver is +1, so N is going to be +5. If you look on the product side, you notice you have NO3 again. The charges are not going to change for the NO3, even if you have more than one of it. Copper is +2 and silver is 0. You could also use table E to look at the polyatomic ions. So if you look at your polyatomic ion chart in table E, you see NO3 nitrate is -1, and there are 2 of them. So the whole polyatomic ion is -1 times 2 is -2. So then copper is going to be +2. It helps you figure out what the charges should be. So copper is going from 0 to +2, and silver is going from +1 to 0. If you look, the nitrogen and oxygen aren't changing, so those aren't being oxidized or reduced. So the element that's oxidized is copper, since it's going from 0 to +2. And the element that's reduced, in this case actually the ion is reduced, Ag +1. There's another one more minute to assign oxidation numbers across the top. All right, so Mn goes from +4 to +2, and Cl is going from -1 to 0. So the substance that's going to be oxidized, that means it's losing electrons again, becoming more positive, is going to be chloride ion. It goes from -1 to 0. And the element that's reduced is Mn4+. It's going down. It's going from +4 to +2. So when it's reduced, the oxidation number is being reduced, going down. And again, notice that when we say what's being oxidized and reduced, we're picking it from the reactant side. So for oxidized, we would say Cl with a -1 charge, and for reduced, we would say Mn +4, because that's what it's starting out as on the reactant side. All right, so next we want to jump into talking about half reactions. So we could break down the whole redox reaction into 2 parts. The oxidation half reaction, which is going to show the atom that's losing electrons or ion that's losing electrons. And for an oxidation half reaction, we're going to write the electrons on the product side. So here's an example of an oxidation reaction. We start with calcium. On the reactant side is 0. On the product side is +2. And we're going to throw our electrons on the product side. For reduction, we're going to show the electrons are gaining electrons. So since they're gaining electrons, they're going to be on the reactant side. So here would be an example of reduction. Ca going from +2 to 0. The electrons are written on the reactant side. I also use this Leo Ger, again, keeping with the arrows, because the arrows are useful. For oxidation, the electrons are always on the right side of the arrow. So the arrow here is pointing to the right, reminding you those electrons better be on the product side. For reduction, the arrow is pointing to the left, to remind you that those electrons better be on the left side of your arrow. So let's look at a half reaction. We'll start simple. Here's a Al plus Ag plus yields Ag3 plus Ag. So let's assign our oxidation numbers across the top. And we'll write our half reactions, first identifying what's oxidized and reduced. So Al goes from 0 to +3. It's becoming more positive. So since it's being oxidized, when you write Leo with your arrow to the right, the electrons need to be written on the product side. I need 3 electrons because we have to always have conservation of charge. The charge on the left is 0. There's nothing but an Al atom. On the right, it's +3. So I need 3 negatives to cancel out the 3 positives to make sure that the charge is 0. Do the charges have to be 0 on each side? No, but they just have to be the same. So since the charge on the left was 0, the charge on the right has to be 0. For reduction, we have Ag goes from +1 to 0. The charge on the left is +1, so I need 1 electron. You don't necessarily have to indicate like 1e minus. You could just write e minus, that's fine. Goes to Ag 0. Also, some teachers might not make students write like 0 for this Ag. It's fine if you just want to write Ag on the product side. For atoms, you don't need to indicate the 0. The important part, though, is that you must be balanced. So the net charge must be equal for each one. So for example, You have Fe goes to Fe3 plus 3 electrons because the charge on the left for the iron atom was 0. On the right, you were plus 3, so you needed 3 electrons to make sure the charge was 0. You have Sn plus 4 or 4 plus 2 electrons goes to Sn plus 2. So you see that it's not going to always add up to 0 on each side of the arrow, but the charges are going to be the same. So on the reactant side, you have 4 plus and you have 2 electrons. And remember, electrons are negative. So you're adding -2 essentially when you add 2 electrons. So +4 minus 2 is +2, and the right-hand side was +2. So the charges are being conserved. It's +2 on the left, it's +2 on the right. So here's another example. And you will see things like this on the reagents where they'll add in a coefficient with the charge. And I know that's kind of challenging for some people, so we just want to look at when you have a coefficient with the charge. So here we have iron 3 plus ion, and there are 2 of them. You need to multiply that coefficient of 2 times the superscript up there. So 2 times 3 is +6. And you have nickel is nothing, so 0. So altogether, on the left-hand side of the arrow, the total charge is +6. On the right of the arrow, you have 2 Fe plus 2. So 2 in front of the Fe, that big 2, the coefficient, gets multiplied by the 2 plus, so that's +4. And you have +2 with the nickel. So +4 plus 2 is +6. So each side is going to be +6. So even though they're not 0, they're both actually +6 in this example. So you don't always have to have them being 0. But regardless, you do have to have mass, energy, and charge conserved. So if the charge isn't the same, it's not, it needs to be balanced. And sometimes the Regents question will ask you to balance that out. So we'll look at an example of that. I like to tell my students this is chem class. In college, chem was abbreviated CEM in some schools. So charge for C, E, energy, M, mass. Charge, energy, mass, CEM, are always conserved in any chemical reaction. They ask that quite a bit on the Regents. So charge, energy, and mass are always conserved. All right, so take a second to look at this redox example. What I want you to do is figure out which one is correctly balanced. If there's a coefficient, that coefficient needs to be multiplied by the charge. You want to see which one has the same charge on the left and the right. Not only that, but the mass, like the amount of atoms, has to be the same. So take a second to try this one. We got a question that just came through the mind asking if when you're balancing an equation, will it always tell you if it's a redox reaction? It probably won't actually. It's just going to ask you in the question which one is balanced. And you have to just know that if you see in any reaction all year long, we have to have mass, charge, and energy being conserved. So here, just make sure that your mass is balanced and make sure that the charge is balanced, whether it says redox or not. So in this example, it's going to be choice 2. So we have on the reactant side a charge of, with the iron, +6. The nickel is 0. So the left-hand side is +6. On the right-hand side, our product side, you have Fe plus 2 is a +4 charge, and you have the nickel, which is +2. So you have +6 on each side. All right, let's look at table J. So if you have your reference table out in front of you and you could turn to table J, that would be good. So another question that came in through the ahead of time, where you guys were able to ask questions, is there was concern about how do you know if something's going to be spontaneous. So if that was you, this is where we'll get to talk about that. So hopefully you're there now, table J. So let's look at table J. Table J was probably talked about a little bit with Miss English, but let's go into it. If any metal that's above hydrogen on the reference table will react with an acid to produce hydrogen gas. So when you're looking at a single replacement reaction, so if you look at the example, zinc plus HCl, if the Zn is higher up than the H on table J, it's going to react to produce hydrogen gas. That would be a spontaneous reaction. So if you look at the next example, we have magnesium and H. So again, if it's higher up on table J, there will be a reaction and it will produce hydrogen gas. So in general, when we're using table J, if we look at the metal side, because there are two sides, there's two columns on table J, you have metals and nonmetals. The more active metal are the ones that are more easily oxidized, lose their electrons. They're going to be at the top of table J. So if you look at table J, which element is more easily oxidized, K or CS? That type of question, you just go into your chart, you're looking which one's higher up. So since K is higher up, that's the one that's more easily oxidized. They could say explain in terms of activity, K would be more active. For nonmetals, the more active nonmetals are the ones that are more easily reduced or gain electrons. So they'd be at the top of the chart. Remember, metals like to gain electrons or be reduced. So F2 is most easily reduced. And that would be at the top of the non-metal side. If you get a question that asks which one's most likely to be reduced and it's a metal, you're going to look at the bottom of the metal chart. So at the top of the metal chart, you're more likely to be oxidized. At the bottom, you're more likely to be reduced. If you're at the bottom of the non-metal chart, those are the less active nonmetals. They're more easily oxidized or they're harder to reduce. So iodine is most easily oxidized since it's at the bottom of table J on the nonmetal side. As far as spontaneous, you're going to be spontaneous if the more active metal is uncombined. So if we look at the equation below, zinc is being added to lead nitrate. The one that's by itself, the uncombined one, is zinc. If the one that's uncombined is higher up on table J, the reaction will proceed spontaneously. So spontaneous means it goes on its own. So zinc, you find zinc and you find lead. If zinc is higher up than lead, then the reaction can happen. So if you look at table J, which one is more easily oxidized, copper or silver? Well, copper will be higher up. So that means that in a single replacement reaction, the copper could replace the silver. This would be a spontaneous reaction. So copper replaces the silver, and then you actually get like silver along that. I don't know if your teacher showed you this. Is a kind of cool demo, but you could get silver along the copper wire. It's pretty cool. So in general, when you look at a single replacement reaction, when one element replaces another element in a compound, we've kind of already seen single replacement reactions, I'm sure, earlier today. But if the element is all by itself, so here, let's say A is a metal. If it's higher up on table J than B, if it's a more active metal, then it will proceed spontaneously and can replace it. Let's say we had a non-metal that was A. The non-metal could replace C if it's more active than C on table J. So take a second to try these few questions related to spontaneous reactions. Got to prepare them ahead of time since I knew there was some questions about it, so you can have at it. There's a question that came through about oil rig on the review. I don't use oil rig, I use LeoGur, but oil rig, just oxidation is losing, even it's just talking about losing electrons, so again, becoming more positive. Okay, so for the first question, which metal will react spontaneously with Al3+? To react spontaneously, it has to be higher up, so just look for something higher up. We got calcium. Second question wants to know, which of the following nonmetals is most active? The most active is at the top of the chart, so of these options, we're gonna go with F. And the third question is based on table J, identify one that does not react spontaneously with HCl. HCl is an acid. I know acid isn't on the chart, but H is. So when we're talking about an acid, we're gonna find H. If it doesn't react spontaneously, it's going to be underneath. So we could have picked something like Cu, Ag, or Au. All right, 2 more questions for you related to spontaneous reactions. Take a second to try them. Okay, so the first one is going to be Ag, which one has the least tendency to undergo oxidation. That means the one most likely to be reduced. And the second one, for something to occur spontaneously, the one that's by itself has to be higher up. So chlorine would have to be higher up than Br on table J. All right, next we're going to jump into electrochem. Electrochemistry, we're basically going to look at 2 different, again, types of reactions, spontaneous and non-spontaneous reactions, where we're going to use electric current and see what's happening here. So first, let's just get into voltaic cells. Voltaic cells are going to produce electricity spontaneously. So voltaic are spontaneous. Okay, electrons are going to flow through a circuit, and that's how we get the electricity that you're probably using to use Remind to text me right now. Actually, Comac wants a shout out, so thanks to all the kids in Comac and everywhere watching the stream, but there you go, Paulina. Okay, voltaic cells are basically batteries. So chemical energy is being converted into electrical energy spontaneously. Electrodes. We need to know that there are 2 electrodes in voltaic cells. We have an anode and a cathode. The anode is where oxidation is occurring. Since electrons are produced at the anode, it's considered the negative electrode. The cathode is where reduction is occurring and electrons are being gained. It's a positive electrode. It's hard to remember the charges for anode and cathode, so we'll talk about acronym in just a few minutes. But we will always use anox and red cat. Some people like to say the red cat gets fat because the cathode gets fatter and the anode gets smaller, but anox means that the anode is where oxidation is occurring and reduction at the cathode. It's super useful. We're going to use it a lot for the rest of the video. Even if you don't like acronyms, most people tend to think this one's pretty easy. So anox, red cat. All right, here is a voltaic cell. There's a lot of information on this slide, but we're going to try to go through it so that you understand what's going on. So we have 2 beakers. We have on the left-hand side half cell 1, and on the right-hand side is half cell 2. We have 2 metals immersed in the beaker. So on the left, we have zinc metal. On the right, we have copper metal. The anode is labeled as zinc, and the cathode is labeled as copper. The anode is oxidation because we have as anox is the acronym we're going to use. So the anode is always being oxidized. To figure out which one's the anode, since it's the one that's more active or more likely to be oxidized, is going to be the top of table J. The cathode would be the lower on table J for the metal side. The cathode, or what's occurring at the cathode, is reduction. In between, or connecting the 2 beakers, are the salt bridge. The salt is just an ionic compound. So we talked about salts, I'm sure, already in acids and bases. We know that since the salt is an ionic compound, moving through that salt bridge are ions. Electrons do not go through the salt bridge. So that's kind of a common Regents question, what happens in the salt bridge or what's going on through the salt bridge. We need to know that the salt bridge is allowing the flow of ions, and it's helping to keep the solutions neutral. So what's up with this wire? The electrons are going through the wire. Electrons go from anode to cathode. So the electrons are going from the zinc to the copper through the wire. The electrons, you see as they move, there's a light bulb. That's like an indicator that this is a voltaic cell because it's spontaneously producing electricity as it moves through the wire. Sometimes you see a voltmeter and a switch. The voltmeter just records, like is basically just showing us how much electricity is being produced, their voltage. So anytime you see V, that would indicate voltaic cell. If there's not a V and there's the light bulb, that's also voltaic. We need to know what's happening though in each beaker. So since the zinc is being oxidized or losing electrons, those electrons leave that metal. So the zinc itself, that strip, the electrons leave the metal and move through the wire. Losing electrons means you become more positive. So the positive ions are going to enter half cell 1. So over time, the zinc atoms enter into the solution. So that anode is getting smaller because pieces of the zinc metal are becoming zinc ions. So atoms, the metal is made up of atoms. They have no charge. Atoms lose electrons. When they lose electrons, they become positive and enter the cell as ions. So atoms are turning into ions in half cell 1. That means like the atom is physically disappearing. It's becoming an ion in solution. The electrons go through the wire, come across the other side to the copper. At that copper on the right-hand side in half cell 2, the electrons enter through the wire coming into that middle. There are positive copper ions in solution. They are so attracted to those electrons, they grab them up. They gain electrons and stick onto that copper electrode. So ions gain electrons, stick on, and are kind of basically plate onto that strip, the copper. So over time, the ions are turning into atoms. There are ions in the beaker. Those ions gain the electrons as they come through the wire and are going to stay on that electrode, the cathode, being reduced at the cathode. They gain electrons and becomes atoms. So ions in the half cell gain electrons and become atoms. Atoms have no charge. So lots of information here, but just try to do the best you can to understand. If you don't fully understand that the anode is always higher up on table J, the cathode is lower on table J, anox, anode is always oxidized, red cat, reduction occurs at the cathode. The electrons always move from the anode to cathode, so A to C, it's alphabetical, and that the ions are what's moving through the salt bridge. And sometimes they don't say wire, they call it external circuit, so the electrons move from anode to cathode through the external circuit. The anode always gets smaller because atoms are being turned into ions, and the cathode is getting bigger because ions are being turned into atoms. All right, so in summary, this is a spontaneous redox reaction. Electrons are going to flow from anode to cathode. It's chemical energy to electrical energy. You're going to see separate compartments. Oxidation occurs at the anode as negative, and reduction occurs at the cathode as positive. As far as the electrolytic cell, this is not spontaneous. You know it's not spontaneous because you're going to see a battery in the pictures. It needs electrical energy to happen. The electrical energy is going to force a non-spontaneous reaction to happen. So you require a battery to work. The cathode is negative in this electrode, and the anode is positive in this electrode. So we tend to use this acronym 8VAN. I don't know if your teachers use it or if you like it, but I find it helpful just to remember what's going on. So 8VAN stands for the anode is positive in electrolytic cells, and V, voltaic, anode is negative. So A, PE, anode, positive, electrolytic, voltaic, anode is negative. The other thing we need to know about electrolytic cells is that the energy is going from electrolytic and electrical energy to chemical energy. And one way that you can remember that is just that electrolytic begins with an E and ends with a C. So it's going from E, electrical, to C, chemical, electrical to chemical, and voltaic is the opposite. So you could remember E starts with E, ends with C, electrical to chemical, then voltaic will be the opposite, chemical to electrical. And that comes up quite frequently. All right, so this type of reaction that's happening in rechargeable batteries. So here's a picture of an electrolytic cell. We could say, what evidence is there in the picture? This is electrolytic. You see a battery right away. You say, oh, this is not spontaneous. Okay, so in this type of cell, the more active metal is the cathode. It's not natural. You need to know that energy is required for this reaction to run. And as far as examples of electrolytic cells, you might have done an activity or lab where you saw electroplating, again, a non-spontaneous reaction, so you would have used a metal. This is a process where you can plate a metal onto another material, like we've seen this in kitchen faucets, silverware, and some cheap jewelry like you get at the grocery store. You could identify an electrolytic cell because the electrodes are both in the same beaker. The substance that's being plated is always going to be negative. That's the cathode. The anode is going to be positive, and that's made up of the metal that whatever it is that you want to plate onto your substance. So here's a picture of an electroplating setup. You see a spoon. We want to plate the spoon with silver. So the spoon is the object. The object in this type of cell is always going to be the cathode. The object is the cathode, and it's negative. What happens is positive ions in the solution are attracted to the negative cathode and stick onto it. They're reduced at the cathode. The ions gain electrons and become atoms and plate onto the spoon. So silver ions are lost from the bar. So the bar, if you look on the left-hand side, is the anode. The metal itself is going to lose electrons. So the atoms turn into ions, and at the cathode, you have silver ions in the solution, gain electrons and are reduced. And that's why the spoon is going to get bigger over time, because those ions gained electrons and became atoms at the spoon. Okay, so here we just want to compare those two cells. Voltaic, the cathode is positive. Electrolytic, the cathode is negative. Anode. So with these charges, again, you could use 8-van to help you figure it out. You need to know that voltaic are spontaneous and electrolytic are not spontaneous. That's why there's a battery to force the non-spontaneous reaction to happen. When you're looking at a picture and you're not sure how to identify them, voltaic, look for 2 separate beakers. Look for a voltmeter. Look for a light bulb or something like that to indicate that it's voltaic. For electrolytic, it could happen in the same solution. So if you see one container, going to be electrolytic. Voltaic, it's chemical to electrical. Electrolytic begins with E, ends with C. It's electrical to chemical. Should know examples of electrolytic cells like electroplating, that the material, the object, the spoon, the fork, the key, whatever the object is the cathode and it's negative, and that the anode is whatever else is in the beaker with it and is positive. In both cells, because this is something that people always forget, in both cells, our acronyms work for everything. So as much as people hate acronyms, these acronyms will work for both. So if you get confused, is it voltaic? Is it electrolytic? Anox, red cat, always. The anode is always oxidized. That doesn't change. Reduction always occurs at the cathode. Doesn't change. Electrons always go anode to cathode. The anode always loses mass and gets smaller. The cathode always gains mass and gets bigger. So anox, red cat will work for both cells. You don't have to worry about that. And electrons are always going to go anode to cathode. All right, so at this point, what I want to do is just go through a couple of Regents questions that have involved oxidation, reduction, electrochem, starting at most recent and going back a few years. Some of it is going to seem repetitive because you're going to start to see that the questions are very, very similar. So in an operating voltaic cell, reduction occurs. So we have anox, red cat. What does red cat stand for? Reduction always occurs at the cathode. All right, next question. Given the which particles are transferred in this reaction? So remember the oxidation reduction reaction. Oxidation, when you lose electrons, LEO, lose electrons, oxidation, gain electrons, reduction. The particles that we're transferring are the electrons. Okay, next question asks which one is a redox reaction? Redox reaction, to figure out that something's redox, it means that the oxidation numbers have to change. So like I said, maybe not the best chemistry way to work this, but easiest way, you have an exam in 2 days. Redox reaction, look for something all by itself. You see something by itself, it's the answer. So if you look at these 4 choices, which one has something by itself? Choice 1, you have magnesium all by itself. Chlorine all by itself. It doesn't matter reactant product side. The reason it's redox is because Mg is 0 on the left, and on the product side, it's +2. So as long as it's by itself on one side, not by itself on the other side, it's redox. Because when you're by yourself, you're 0. In a compound, you're not going to be 0. You're going to have some charge. So magnesium is oxidized, goes from 0 to +2. Chlorine is going to be reduced 0 to -1. In all the other reactions, you're not going to see a change in oxidation number. So for example, if in choice 2, calcium is +2 on the left, +2 on the right. H is +1, +1, O is -2, -2. It doesn't change. Redox means it's the oxidation numbers must change. Something has to be oxidized and something has to be reduced. Alrighty. Next, this is a short answer from January 2016. It says, explain in terms of energy why the artificial leaf is an electrolytic cell. So in terms of energy, so that means in your answer, please write the word energy. So electrolytic begins with an E, ends with a C. So we said that energy is going to go from electrical to chemical. That's the easiest way to help you remember at this point what's happening to the energy. But remember that electrolytic cells have a battery in them, so they're going to be requiring some type of external energy source to force the non-spontaneous chemical reaction to happen. Next question wants to know, state in terms of oxidation number of oxygen represented in equation 3. So in equation 3, we have oxygen on the reactant side is all by itself. So that means it's going to be 0. On the product side, oxygen is in a compound. It's not any exception. It's not a peroxide, not with F, so going to be -2. So oxygen goes from 0 to -2. Okay, so that was the last one, January. Moving backwards, August 2015. In a redox reaction, remember redox means oxidation reduction, just put into one word. The number of electrons lost is always equal to the number of electrons gained. You have to have conservation of charge, energy, mass. The number will always be the same. All right, at which electrode does oxidation occur in a voltaic cell and in an electrolytic cell? So it doesn't matter whether it's voltaic or electrolytic. We said that anox and red cat will always work. So the anode is oxidized. Red cat reduction occurs at the cathode. What is oxidation? Oxidation is where you lose electrons. So they're asking where oxidation occurs. So oxidation will always occur at the anode in both the voltaic and the electrolytic cell. All right, here's another picture from that same exam. And it says, given the diagram representing an incomplete electrochemical circuit, they say solid copper will be deposited on one of the carbon electrodes when the wires are connected to. Right away, you want to look at it and say, this is only one container. There are not two separate compartments. One container means it must be an electrolytic cell. For it to be an electrolytic cell, I need external energy. I need to have a battery. So choice 2. Okay, August 2015 short answer question. Question 83, there's like all this reading. We don't have a lot of time left, so I just want to look at what's happening here. They say, state why early scientists classified the reaction represented by equation 1 as oxidation. There will be some questions on the regions that you could find the answer right from the reading. So if you look at the first sentence, it says, early scientists defined oxidation as a chemical reaction in which oxygen combined with another element. And that's true. Early on, they didn't know what the first definition of oxidation was, combining something with oxygen. So now we know more about this transfer of electrons, but that's all you would have to say was scientists defined it as anytime oxygen combines with another element. 84, determine the change in oxidation number of carbon in equation 1. Okay, so we look at carbon on the reactant side. We have hydrogen as +1 times 4 would be +4, so carbon is going to be -4. And on the product side, you have -2 for oxygen times 2 is -2, so carbon would be +4. All right, 85, write a balanced half reaction for the oxidation that occurs in the reaction represented by equation 2. So first you would want to assign your oxidation numbers. On the reactant side, magnesium is going to be 0. Sulfur is going to be 0. They're uncombined elements, so they have an oxidation state of 0. On the product side, magnesium is in group 2, so it's +2, and sulfur is -2. So magnesium is going to go from 0 on the reactant side to +2. Since it's becoming more positive, it's losing electrons, it's oxidized. We would write magnesium goes from 0 to magnesium +2 plus 2E-. The electrons have to be on the right side of the arrow because we drew our Leo before with our arrow pointing to the right to indicate that the electrons are going on the product side. June 2015 multiple choice asks, what's the oxidation state for an Mn atom? And manganese is, when they see Mn atoms have no charge, so you're going to pick a 0. In a redox reaction, which particles are lost and gained in equal numbers? Redox, reduction, oxidation, lose electrons, oxidation, gain electrons, reduction. So the particles lost are electrons. All right, next, 83, state the direction of electron flow. It's from June 2015 as the cells operate. What you want to do is electrons always flow from anode to cathode. So you have to look on table J to figure out which one is the anode, which one's the cathode. Zinc's higher up, so zinc is the anode. Electrons flow from zinc to copper. You could also use the equation to see that zinc is becoming oxidized, is going from 0 to +2. So the half reaction 84 for the oxidation would be Zn0. It's by itself, arrow, Zn2 plus 2E-. The electrons have to be on the right side because oxidation, again, the Leo, the arrow pointed to the right. 85, explain why phosphoric acid is needed for the battery to operate. If you notice, this is a voltaic cell and there's no salt bridge. So you could have mentioned something about the phosphoric acid is needed to be, because you need an electrolyte or some type of salt to keep the cell functioning. You could have also talked about how phosphoric acid provides the hydrogen ions that are then going to be reduced in this reaction. January 2015, the chemical process in which electrons are gained, GER, gain electrons reduction. Which process occurs in an operating voltaic cell? Voltaic cells are spontaneous. Chemical is being converted into electrical. Remember, electrolytic, E to C. Voltaic is the opposite, chemical to electrical. Determine the change in oxidation state for oxygen. On the reactant side, oxygen's all by itself, 0. On the product side, there's no special exception with iron, so -2. All right, what's the oxidation number of manganese in KMnO4? Oxygen is -2 times 4 is going to be -8. K is in group 1, so it's +1. So Mn would have to be +7. As aluminum loses 12 moles of electrons, the oxygen, we know the number of moles lost always equals the number of moles gained. So if 12 moles are lost, 12 moles of electrons are going to be gained. Okay, June 2014 short answer. We want to identify the particles that flow through the wire. Well, what's going through the wire are the electrons. Electrons always go from anode to cathode through the wire. All right, 63 is to balance this equation in your answer booklet. The equation is right under the picture of the cell. You have Zn plus Fe plus 3 goes to Zn plus 2 plus Fe. What you want to do is make sure the charges and mass are balanced on each side. So since the charge on the left is +3 and the charge on the right is +2, you're going to multiply the iron by 2 on the reactant side and the zinc on the product side by 3. Since you're multiplying the zinc by 3 on the product side, you'd have to put make a coefficient of 3 for the zinc on the reactant side. And since you multiplied the iron by 2 on the reactant side, you'd have to put a 2 in front of the iron on the product side. 64, identify one metal from table J that's more easily oxidized. More easily oxidized means higher up on table J, so just pick something above zinc. A whole bunch of answers would suffice there. 65, explain in terms of zinc atoms and ions why the mass of the zinc decreases as the cell operates. Okay, zinc is the anode. We know zinc is the anode because it's higher up than Fe on table J. Zinc atoms are turning into ions. That's as simple as you can make it. Zinc is oxidized, which means it's losing electrons. So zinc atoms become zinc ions. All right, multiple choice, January 2014. In an oxidation reduction reaction, number of electrons lost is always equal to the number of electrons gained. I bet you got it by now, hopefully. What occurs in an electrolytic cell? E to C, electrical to chemical. What occurs at the electrodes in both the electrolytic and voltaic cell? We have anox, red cat, and we need to know that oxidation is, use your other acronyms, Leo Ger. So oxidation occurs at the anodes as electrons are lost, choice 2. Which one reacts spontaneously with H? You're just looking for anything above H. But we're pretty much out of time. But you see that at least the types of questions that were asked. So if you have any questions, please definitely ask. You could keep the questions going through the Remind feed. I'll answer you back. But good luck on your regions. Thanks to David Konofsky for organizing this and all the other people. And good luck to all the kids out there, not just in Comac where I teach, but everywhere in New York. And I'll pass it over to Ms. Drury. He's going to take it over for organic and nuclear.